After 9 o'clock.
Yeah, I noticed it was still very light at 7:30.
I think we're live, gentlemen. Just caught us in the middle of a skull session among the brainstormers, or the brain trust, if you will. Hello, stargazers. If you're part of that crowd that showed up at Farron Hall on Friday night, we loved having you, and I hope you join our club. Welcome aboard South Coast of California's longtime Astronomy and Telescope Club's weekly Monday morning vlog podcast, the SBAU Astro Hour, our 112th time at bat here online get together using Zoom, and the big bad brain trust around us here for the Santa Barbara Astronomical Unit, which is a diehard stargazing group of people like the leader of the local theater organ society, some retired physicists, and myself. I'm not even going to tell you what my background is. My name's Ron Heron, Vice President. I'm going to host, and we're going to talk about the waning. Is it waning again? Waning gibbous moon.
Yes.
We can blame that gibbous moon for all the wane we've been having. How do you save fuel with a space probe? Why you use gravity? We're going to talk about it. It's, I think, free energy, I guess. Last look at the winter sky. Got a shot of Jupiter at an unusual angle. Very colorful picture we'll see this hour. Double stars, real ones, and wannabe stars. I'm not sure. Is this a Rona Barrett hour? Anyway, the distant Rubens galaxy, named for a guy named Rubens. Boy, it's a monster.
You're a Reuben. It's a lady.
Oh, it's a lady. I read the name.
Yeah.
I didn't realize it was a lady. She discovered it.
Her first name is Vera.
That's right.
Okay, I didn't read that part, or I would have said. Anyway, we're going to look at our own galaxy center and discover a big arc, a radio arc there. And the web focuses on Uranus. Oh, wait a minute. That's your proctology.
Did you really mean to pronounce it that way?
Gentlemen, let's meet you. Mr. President, on my left in white,
Hello.
winner of the annual Santa Claus Lookalike contest again in Santa Barbara. Congratulations. In front of the Ukrainian flag is our outrageously outreachable outreach coordinator, Mr. Chuck McPartland.
Morning.
Wife, if we're lucky, Pat, is our merchandise manager, and we'll join him at his side. Certainly the cats he's allergic to will. Having joined us early is a man with a beard, another beard. We got two beards. I started shaving mine. Here is the president of the Santa Barbara Theater Organ Society and one of our longtime members, Bruce Murdoch. How are you, Bruce?
Oh, I'm doing fine.
Could give you guys wives you guys showed, you and Bonnie. And Jerry brought Pat Forgy, and Chuck was there with Pat. And we missed this other guy here who smells like sourdough bread. He's a definite veteran of Westmont College, one of their beloved science instructors, Tom Whittemore, who edits
Morning.
Santa Barbara Astronomical Unit newsletter. And you do a good job, and you can read the president in there every month. And we try to start the hour every week. We do this 4 times a month, and we've been doing it over 2 years. We're in our 3rd year, ladies and gentlemen. This is number 112 for the morning of the 10th of April, 2023 to the 16th. It's time to have a little laughter here. This is award versus punishment. Can you enlarge that a little bit? Doing the same thing. It's the same girl. At different ages, different stages of her life. As a schoolgirl, she gets an F because she's spending all her time staring into space. And as a grown lady, she's an astronomer and gets an award. Astronomy conference, same thing. This is for spending all your time staring into space. Congratulations. And this one I liked, and I came up with an alternative for it, gentlemen. Space-time continuum. In 4 panels, 4 boxes, or you could look at it this way. The man has arrived at the 10th floor in the left picture, and that's his arm sticking out of the door of the elevator on the 1st floor.
Ouch.
We might want to use that as a topic and see how that ties into the space-time continuum. It looks very, very quantum to me.
This also suggests quantum entanglement, but that's another story.
Okay, well, it's funny. And this one is from the past.
Oh, did I show this before?
Time flies, yeah. Don't kill us.
Okay.
We come from the future bearing an urgent message. Those are time flies that have arrived. Okay, it's been a while. This is also a past one. All right, they're boarding the spaceship, I guess, ready to get launched. One guy stops and says, Bob's on his, why, you took it away from me.
Oh, sorry, I thought it was.
Well,
There you
I
go.
haven't seen this one, I don't think. Bob's on his way, guys. He didn't get the email about the gate change. Do we get that? What gate change? What are we talking
Well,
about?
at the airport, your gate changes sometimes and you have to run to a new area.
God, that happened. Boy, does that touch a nerve. These are two ancient Roman aliens. One of them talking to the other. Let's take the flying chariot to the forum and abduct a few citizens.
So
And
if
it's
you know
Area
your Roman
51.
numerals, you know this is Area 51.
Oh, that's what LI means. All right.
Yeah.
You're right. Somehow, I wonder who came up with that version of aliens. And here's Calvin and Hobbes. Which one is Calvin? Is that the kid?
Yeah.
Yeah, the kid. This is
Right.
Hobbes.
Hobbes is the tiger, and the kid says, I don't think math is a science. I think it's a religion. And Hobbes goes, a religion? Yeah, all these equations, they're like miracles. You take two numbers, and when you add them up, they magically become one new number. No one can say how it happens. You either believe it or you don't. The whole book is full of things that have to be accepted on faith. It's a religion. And Hobbes goes, and in the public schools, no less, call a lawyer. The kid says, as a math atheist, I should be excused from this. From
He's
one
always
math-
looking for ways to get out of his homework.
All right. Okay, these are two ladies who are about to go through an airlock to get outside the space station. And one of them notices she's wearing the wrong backpack. The Bible pack has a little bear on it, and it's purple, and it's obviously her kids. Crazy morning. Did I grab my daughter by mistake? Here's two dogs on the moon in spacesuits, making sure that all the wolves that were their predecessors went to their graves, not knowing this. You know what? It's a rock up here. All this time, we've been howling at a damn big rock. That's funny as hell. I love that. All we need is the monolith. Okay, now here's a violence about to happen. This would be, which one is it? The groaner? No. Oh, a couple cops on the street witnessing a car from the Cubic Earth Society. Tell me there's no Cubic Earth Society, but you made that up. And they're about to have a rumble with the Flat Earth Society, people that live right there. And looks like we may have a mindless outbreak of violence, guys. Yep,
You've certainly got the mindless.
there is no cubic. Nature doesn't do cubes.
Sure it does. There are some crystals that form cubes.
Right.
Pyrite.
I thought
Right.
they're mostly six-sided, hexagonic. It'll do hexagons, and there's one on.
No, there
top,
are crystals.
Salt is a cube.
Salt's a cubic.
but not in space.
Well,
I
no,
mean,
the minerals, the face center cubic, you can body center cubic, you can have a tetrahedral. There's all kinds of
Okay.
shapes for crystal structures.
if you had a planet-sized cube, you'd have what, 8 or 12 really big mountains? The
8.
corners?
There are 8 corners on a cube.
Is there 8 quarters? 1, 2, 3. Yeah, you're right. Okay.
Be the
Very
board.
good.
No, there's 6. Oh, 8 corners. Yes,
There
corners.
are 8 corners. There are 6 sides.
Yeah.
That's true. You're absolutely right. Can't be done. But let's go to the moon, and here's our president guiding us through it. A great hour. I learned so much.
Okay, this is a map of the moon, not a photograph. And it is the phase for this evening, a waning gibbous moon. And I've written in Tycho down here, which is this crater with the hand on it right now. Tycho has, if you look at the actual moon, you'll see that there's a big ray system that goes out from this, which gives the moon the appearance of a navel orange to my eyes. But it
Wow.
draws your attention to the this scarp over here near Mare Nectaris, which is the feature for tonight. Now, this moon is tilted 90 degrees from that one, but this is what it actually looks like. Not a map, but this shows the rays that go out from Tycho. So it's very easy to spot.
That was one big asteroid, wasn't it?
Yeah.
It was a fairly recent one, I guess, and it had a lot of talcum in it. So
Yeah.
which gives
I
you.
always find it interesting to compare that to Tycho, which in your previous picture was off to the left and up a little bit.
That
Because
was,
there, the rays, rather than being straight, are very wobbly. So that was a low speed impact, and the ejected just sort of rolled around and left
Oh,
trails.
you mean Copernicus, which is the one on
I'm
the
sorry.
left.
Yeah, I'm sorry. What did I say?
You said Tycho.
Tycho.
Yeah.
Oh, okay. Sorry. Tycho's down below.
normally, yes, but on this picture, Tycho's this one to the right.
Right.
That's why I said this one is flipped 90 degrees from this one.
Right.
So Tycho is right there.
Copernicus is there. Yeah.
Yeah. So let's see if
Marys,
I can.
the Marys are seas, and that means they are what? Vast fields of lava that flowed and buried all the craters that were there before? Or
Yeah, pretty much. Pat just piped up. She's a lunar expert. She said the rock that made Tycho was about 6 miles across, so comparable to the one that killed off the dinosaurs.
Oh,
So I think it's safe to say that there will be no dinosaurs found on the moon.
Yeah.
Right.
you never know what they'll dig up on the moon.
So a lot of features stand out in this shadowless area over here. There's the edge of this scarp here, and then there is the Mare Nectaris. Let's go to I disoriented myself to the Altai scarp, which is a different scarp from the one I pointed out. And this is Mare Nectaris. And this is an old lava crater that has been flown over by the lava sea that Mare Nectaris represents. Now you can see that there's a lot of, there's some semi-flat regions in these craters up here, but there's a lot of little craters in them, which means that these are probably older than this is. And so this has more craters. There were several, as I'm sure you know, there were several bombardment effects or eras where there was heavy bombardment, and then there was relatively little, and then there was more heavy bombardment. Try to find the time scale for that sometime.
But as we all know, the far side looks nothing like this. It's nothing but craters.
Well, it doesn't have the big seas, but this
Yeah.
Altai scarp is one edge of a very old and very large crater, an impact zone, and it actually defines the edge of Mare Nectaris.
Well, we got some pictures though, didn't we, of the other side during Apollo?
Yes, we did. First, the Russians got a first picture of it.
Did
But
they really?
once we had, what was it, Apollo 10, I think, orbited the moon.
Apollo
without
8, I
landing.
think even. Apollo 8, I think, was the first.
Was it? Okay.
But the first image of the backside was, yeah, one of the Luna probes from the Russians.
Right. And I think Google makes a Google Moon application that shows the complete all the parts of the moon.
But now, do we have a field of names for the other side?
Of course, yeah.
Yeah, it's all named, mostly
Really?
Russian names, the
Oh,
big stuff anyway, because the resolution wasn't very good on their camera.
Mhm.
well, we're about to send 4 people out on Artemis 2. Is that next year or this year? Did you see those guys? There's a lady.
Yeah, they named the people, but I think it's 2 years away.
Oh, is it 2 years? It's a Canadian.
Yeah, they do not have a lander yet. So
No, that'd be Artemis
they
3.
need to finish development of that. That award went to SpaceX, and they need to finish developing it, and they need to demonstrate it. So it will land on the moon empty several times before they put people in it.
Okay. Wow.
Yeah, if Elon's doing it, I think it's going to take a while.
Yeah, he's very optimistic on his estimates of time.
Well,
And you never know, he might get distracted and spend 40 billion on something else on the way.
Yeah.
He is an impulse shopper.
But NASA's concentrating on the South Pole, right?
Everybody is, yes.
Everybody's
For,
on the
for permanent basis.
That's where the water is.
It's where the water is, and it's where potentially long or permanent sunshine is. So you can put solar cells up on the top of hills and mountains, and you can down in the valleys, you can get at water ice and use that.
Doesn't it have lava tubes too that you can get out of the radiation?
I don't know that I don't know of any lava tubes at the South Pole, but that would be a good thing to look for. We'll try and get some pictures of the South Pole that are straight down. The lava tubes I know about are pretty much up here on these, the rills on the side of the moon that is facing us.
Yeah, the big mares,
Yeah,
because that's where you had all the lava action.
yeah. So, but we'll look into that. Good idea. Okay. So now we're going to look at gravity assist.
Here we go.
This is how things get thrown out of the solar system. This shows Voyager 1 and Voyager 2's a cartoon of their paths, not in any great detail. But this little ring in here is the Earth's orbit. And Voyager 1 was launched after Voyager 2. So Voyager 2 was launched first in August 1977. So it went out, it swung by Jupiter, and it swung around Jupiter, which picked up, so it picked up speed and a little change in direction, and then it went by Saturn fairly closely. So it had a significant change in direction and a significant increase in speed. And then it went past Uranus, got some great pictures, and went out past Neptune. Uranus gave it a good change of direction and more speed and headed on out. The same effect happened later to Voyager 1, passing Jupiter, passing Saturn. It did not go by Uranus.
It actually beat Voyager 2 to Jupiter.
Oh, you're right. But yeah, but on that path.
Yeah.
So
even though it was launched second.
Yeah.
It was launched, yeah. So it went out, it missed Uranus and Neptune, but it still had significant speed increase from going by Jupiter. And so it's headed, these are both now out of our solar system. They're past where the solar wind keeps any interstellar wind and magnetic fields away. At the point they're out there, it's weak fields, but it's still a significant flow of particles. They've noticed a radiation increase for each of them as they enter interstellar space. And as the sun gets more and less active with the solar flares and stuff, and their mass ejections, the boundary with interstellar space fluctuates and moves in and out a little bit. The key thing is that this is the same effect you get when you play pool. We had a great speaker that explained this at our club about 1.5 years ago or 2 years ago. And if these were solid billiard balls and you aimed one at Jupiter, you can make it careen off. If you hit it at the right angle, it will careen off in this direction. Now that one is due to conservation of mass and energy from a conservative, meaning it conserves energy, collision. But in gravitational assist, we're not going to collide with it. We're going to swing around the back of it, but the same thing holds as if there were a collision. You still get conservation of momentum and energy. So
it actually still, I think Ron or somebody said earlier it was free energy. No, you're actually stealing a little bit of energy from the planet.
That's right.
Really?
Yeah. So
you can not only use it to speed up, but you can use it to slow down when you launch toward the inner solar system.
Yeah. And you have slowed Jupiter down slightly by picking up speed yourself. But the ratio of masses of Voyager 1 to Jupiter is not something we're going to worry about.
Okay, so, but it doesn't take it away as it goes by. It sucks it in, and it doesn't suck it back and take it all back. Somehow
it's like a kid like David with a slingshot, that Goliath, he whips it around and then he lets go. The rock takes off at a high speed. Headed toward a neutron. What's that?
Ron, it does accelerate as it's coming in because the gravitational field, the force increases, and it does decelerate as it goes out, but you suck some of the rotational energy out of the planet.
Yeah, you have a net gain.
Yeah.
Really? It doesn't take it back. But now, are they past the Kuiper belt and into the Oort cloud?
No, not even close.
They're not even in the Kuiper belt, so they're still in the
They're
solar.
in the Kuiper belt, but they're not out of it.
Okay, well, here's a question that I've wondered all my life. Is there no friction in empty space, interstellar space? Are these two going to just go on and on forever at the same speed, or might they slowly slow down running into atoms and things like that, hydrogen?
Well, you've asked several questions there.
Yeah.
Well, no, it's, I want, is it
Rather than friction, I would say there is wind resistance, you might say, because if you run into things, grains of sand, molecules, all sorts of things. And as a matter of fact, if we extrapolate that, I've always thought that interstellar travel at close to the speed of light would be impossible, despite what we see in Star Wars and Star Trek, because you would run into so much stuff that it would just erode the outside of your spacecraft away at the speed that it did it.
That's why you need shields.
Yes, that's why you need shields.
They have a big magnetic field in front of the ship.
But even if it didn't damage your ship, you would bouncing it off, you would lose energy. So,
well, are they aimed at different stars that we know for if they keep going?
they're not aimed at different stars. They happen to be heading toward a star probably, but I don't know what it is.
I think Aldebaran is one of the stars that one of the Voyagers is heading for.
Okay. So people that criticize Star Trek always criticize the fact that Scotty, the engineer, was always saying, you know, I don't know if I can maintain this speed, the engines can't hold, or something like that.
Yeah.
And then people point out if you turn the engines off, you'll cruise at the same speed. But I think at that speed, you actually wouldn't. I think the friction with the environment would slow you down. So they might have been very, what is it when you predict correctly?
Prescient.
Prescient, thank you.
Well, when I'm driving around town, I quote Picard and I go, warp speed, engage.
Engage.
No, engage warp speed to get us through this traffic light. Here they are.
Make it so.
Make it so, that's right, yeah. So these are spacecraft that we have launched that you have used or made use of. I got the
Gravity
typo a little bit up there. So far, Luna 3, Pioneer 10, 11, Mariner 10, Voyagers 1 and 2. We just saw their paths. None of the rest of these, to my knowledge, have actually got out of the solar system. Galileo, Ulysses, Messenger, the one famous one that went by Mercury, Cassini, Rosetta, New Horizons, that's the one that went out to Pluto and then got gravity assisted from Pluto and headed for another Kuiper belt object out there. So that one is definitely exploring the Kuiper belt. Juno, which is now at Jupiter, the Parker probe, solar Parker probe. And that is an example of what Chuck was saying, that you can use it to slow down. So it's just as tricky, maybe even more, to slow your spacecraft down from Earth's orbital speed to get it to, so it can rotate or be in an inner orbit, a lower energy orbit, and orbit the sun. The solar orbiter, ditto, Bepi Colombo, and recently Lucy.
What the heck is Bepi Colombo?
That's a mission to Mercury and Venus, I think.
Who set it up? That doesn't sound like one of ours.
That's the European Space Agency, and it's primarily an Italian mission.
Oh, got it. Well, it's got to be critical about how close you come to the planet. It's because it changes the trajectory and its angle around the planet, right?
Mm-hmm.
And the speed of rotation of the planet. So they all have to be taken into consideration.
And whether you go toward the leading edge of the planet in its orbit or the trailing edge too.
But do they correct after the fact as the thing has gone by the planet? Do they turn on some of the rockets to straighten it out and go?
They frequently do mid-course corrections, little ones if they're needed. A lot of these things recently, especially heading for Mars, they are so accurate they didn't need any mid-course corrections that I know of.
Wow.
Yeah, and they calculate very carefully what they're going to get from the close pass. So it's not like they have to immediately do some correction.
Well, I'm assuming we saw all this in different sci-fi novels, but I haven't really seen it in Star Trek or any TV, talking about gravity assist.
Sure. There's the Star Trek where they travel back in time, where they, zoom very close to the sun and pick up a whole bunch of speed. And they use it to go backwards and forward in time.
I think one of them actually dipped into the sun.
Yeah.
Oh my God.
The sun is not very dense. Let's put it that way.
Huh.
I was going to say, Chuck, I just saw that tomorrow.
Saw what?
Yeah, you saw that
I just saw
tomorrow.
that
Never mind, I get it.
tomorrow.
Okay.
I was hoping the president would show that cartoon about looking through a telescope and just look at it. It sounded like the Groner one. Remember that? The Groner. I never mind. I can't remember what it looked like, but
Yeah, that one was late last night, I think, or something, and I didn't have time to put it in our list. It'll be next week.
Next week we'll dedicate it to Tom Whittemore.
Okay. So this is the night sky in the west at 8:30 tomorrow night.
On Wednesday.
Yeah.
Wednesday, you're right. You're right.
Mhm.
And this shows Mercury, Uranus. Venus is in the Pleiades. That'll be a nice astrophoto.
It was pretty nice last night, although not as close as it's going to be.
Yeah.
Yeah, and Mercury is very easy to see now in the west.
If you've got a good west horizon,
We do.
Tom's always bragging about being up on a hilltop over there.
Yeah.
The rest of us eat our heart out.
So Venus is in the Little Dipper.
No.
No, it's in the Micro Dipper.
Oh,
Yeah.
I thought Pleiades were Little Dipper.
No,
Little
Micro
Dipper
Oh,
is
no.
Ursa Minor, the little bear where Polaris is at the North Pole.
Okay.
Yeah, it's the end star on the handle of the Little Dipper.
Yeah. We're not really saying goodbye to the winter sky. It's just slowly evolving.
Yeah. Oh, and yet, no, we're saying goodbye because this is early in the evening and all these constellations are bright star winter constellations like Orion, Pleiades, and they're about to set, and then they'll be in conjunction with the sun, and then probably late summer or midsummer, they'll be rising in the east again. So that's why I put down goodbye.
When do you suppose the next time we'll see all the planets lined up like we have recently?
Now that's there's two ways what you mean in line up. In the sky, they're all on the ecliptic, so they all always line up. You can draw a line to cover all the planets all the way around the sky. To be truly lined up on one side of the sun, and you look down on it, you see them roughly in a line. That I think happened in 1964, and maybe since then, but I don't remember.
It's much rarer.
Yeah. Because I was in college in that time, and I remember that. Okay.
All right, where are we going now?
Oh, I think I got these in reverse here. There we go. Okay, now this is higher up in the sky and later at night, a half hour later. So we are looking at this star, Cor Caroli, which is a very nice star. This is a true binary star. This is the Big Dipper up here, Ursa Major. The Little Dipper is off in this direction, along with Polaris. So Polaris is in this direction. That's north. This is south. And the one I've never heard of before, called Upgren 1, has been considered to be, was discovered recently, I guess. Let me just go back here. This is Cor Caroli, which is a very slight bluish star, and this is a yellow goldish star, but this one in this picture, this is overexposed, so it looks white, which is unfortunate, but they're very different in brightness, and so it's hard to get the two with full color. And that's a true double star. The other one,
Binary, true binary.
Binary, excuse me, yes, God. Okay. So these, there's a triad of stars that this whole feature has been called Upgen 1 and was believed to be the end of a star cluster. Everything else has drifted away. And it was a true multiple star system. But since then, data has been taken that shows that these are just a chance position. So it is what I put down as a double star or multiple star wannabe, but it didn't make it. It's very hard.
These are far enough apart, they're not gravitationally bound.
That's correct.
Yeah.
So
Well,
they're
it's the
all
same thing about, Alberio. For a long time, they thought it was a gravitationally bound double star with a rotational period of about 500,000 years.
If you
But
can
they've
see,
now discovered it's over 300 light years separated, and one doesn't know the other one's there.
if you can see them easily in an amateur scope, they're probably not a true binary. So this bullseye is centered on Upgen 1. My planetarium software did not have it in its catalog, so I tracked it down with right ascension and declination. So it's just a hop, skip, and a jump from Cor Caroli, which is a more famous but fainter version of a binary star of dual color.
But you listed in your talking points as an asterism.
Yes, it's a true asterism.
But I thought asterisms were like small constellations. You could see them, but they're just tinier and littler. This one you can't see without a telescope, can you?
But that doesn't erase the fact that it's an asterism.
Yeah.
So that's the asterism. Do asterisms form a shape like
They do if you want to find one in it. So
kind of looks like a Christmas tree or a small Orion.
it's definitely a Charlie Brown Christmas tree.
Yeah.
Could be a howling dog.
Yeah.
It doesn't really speak to me very much there.
Slice of pizza.
Yeah. Yeah, the triangle down here is very distinct.
So they're not orbiting each other. They're going to go their merry way and separate.
They're all individually orbiting the center of the galaxy.
Okay. But since we have binaries, we have a few singles. What's the maximum number of stars they've found that are orbiting each other?
Well,
about half of them.
Yeah, it's roughly 50%.
Well, I mean, there are three trinaries, right? That would be three.
There are ones that have 6 that are known, and probably 8. It tends to be in binary or groups of 2 in even numbers, because you tend to have subgroupings that are close that then orbit each other. So two stars that orbit another pair of stars, and then in turn is orbited by another pair farther out. So you tend to have even numbers.
But I suspect there's an inverse relationship between the number of stars and its popularity or occurrence.
Population, yeah.
So the more stars there are, the less likely it is to form.
If you hit 6 or more in the same general area, you've got a cluster then probably.
I guess you could call it that, yeah.
I mean, we've talked about some small clusters, and then there's others that are...
Globular clusters are orbiting in a complex way. They're orbiting as common center.
Would that be a definition of a cluster? All the stars are sort of mingling together?
Loosely gravitationally bound, I think, is enough to be a cluster.
Yeah.
Okay, and some of them have a black hole in the middle of it, I think.
A couple of the globular clusters do.
Yeah, if they have a black hole, they're more likely to be gravitationally bound to the black hole.
Okay, fantastic. Good stuff, Mr. President.
Okay.
Where are we going next? That picture of Jupiter. You didn't give much to talk about, but it says it all.
I put some in just because they're pretty pictures.
Yeah.
This is North Pole, South Pole of
Don't
Jupiter.
know, just a picture.
This is
But
just
it was taken from Juno.
And this is like a mid-latitude region.
Yeah.
I would say the equator area.
But what gets me, we have clouds in our sky. So our sky is blue or some shade of gray. And the water doesn't really, it sometimes mixes with the sky, but sometimes it's there as an object. But look at all the complexity here of things that don't mix and blend into. Here you'd have greenish brown and blue that would supposedly mix. Why do these colors stay so separate? Obviously, some chemicals are immiscible in each other, or maybe they're at wildly different altitudes. But
Mhm.
on the edge, you don't see any structure. It's just one curve. So implying that the top of the atmosphere is all at the same level.
Yeah, it really isn't though. I mean,
No.
some of these features are deeper, but
Yeah.
then you have a transparent layer above it.
Something about Jupiter I've always wondered. Now, if you were orbiting Jupiter, you would be weightless, just like orbiting the the Earth. But if you were in one of those balloons they hope to put, and you're sitting there in the top of the atmosphere of Jupiter, you're going to weigh a lot in that capsule, aren't you? You're going to.
Well, you're far from the center.
No, I mean that there's a lot of weight.
Now it is, but weight is only exists when you resist the fall. So if the balloon is in the atmosphere, then it's got buoyancy and it's keeping you up. So you would feel weight of the balloon pulling you up.
Yeah.
So you would feel weight against the bottom of the capsule, but you would also be buffeted by the winds because you'd be subject to the wind. You would not be in orbit. The balloon does not orbit unless it's out in outer space.
Yeah.
By the way, they're thinking of making a hotel out of a ring of metal with each room as a balloon.
Yeah.
Like I'm going to spend the night in a balloon in space with meteors flying around.
Well, and also, Ron, if you were in this upper atmosphere of Jupiter in this balloon, you're far from the center. So you might only be feeling 1G.
Yeah.
Really?
Yeah.
I mean, you could put how many Earths inside of Jupiter?
1,300, but you're far from the center. And it's 1/r squared. And it acts as though it's a point at the center. Although it's so big that you might be feeling sideways gravitational forces from other stuff too. So it's a little more complex, but you're not necessarily feeling the entire gravity, like you would if you were down near closer to the core of Jupiter.
Yeah.
When I was a kid and first got into astronomy, they had a chart in one popular book, and it showed how much you'd weigh on the surface of each of these planets. And they had a surface for Jupiter, and that if you were standing on the surface of Jupiter, it had an atmosphere as thick as the Earth's. So it was so solid underneath, you'd weigh 12 times what you weighed on Earth. But of course, we've learned since then, Jupiter doesn't have a solid surface and interface. It has the solids and the gas, but it has a smooth transition between them.
Be a great place to put a Jenny Craig weight loss program, wouldn't it?
No, yeah. Okay. So now we're moving to the James Webb Space Telescope.
Oh,
And here it's taking a picture of Uranus.
planet that's different, wants to be different. It's going to turn on its side, spin sideways.
Really complex ring structure.
Well, there's supposed to be 2 inside rings that have only been seen by a Keck observatory and I guess Voyager, right? Did this see it?
Well, that's what you're looking at.
Yeah. 1, 2, 3, 4.
See
5.
5
I see
ring.
5 rings. It has 7 rings, but they don't all show here, I guess. This is like the one they took a few months ago of Neptune. Because we have infrared contributing to this, we now see structure. In visible light, this would just be a solid blue dot or surface.
The circle would be blue, even though it's infrared as far as the telescope.
Well, these are false colors. They assign colors to each filter. So we can make it, pink and chartreuse, whatever anyone likes. The planet also has 27 moons. And here is from the near infrared camera, which actually covers what in the industry we call the infrared. The ones that are bluish, warm colors, that's through the filter F140M. And things that are red here is through the filter F300M. So it distinguishes the moons from the background stars. This does not show all 27 moons. You see 1, 2, 3, 4, 5, 6.
And these are the Shakespearean characters.
Yeah. These are, this was I think this was a 10-minute exposure. So a lot of the moons are too small, 12-minute exposure. So the others
All
are
those moons are in that vertical up and down plane.
Pretty much.
They turned over too when it was turned over, all the moons.
Yes, because this happened early in its history.
It doesn't actually turn over in a physics sense. It turns over because it's like flying sideways, and after a while it comes back the other way. But the axis that it rotates around has angular momentum, and that does not flip. That's just permanently at what, 89 degrees or something?
Yeah. No, but Ron's question was about the orbital plane of the moons.
Oh, yeah.
Being also tilted, so that it conforms largely with the equator of Uranus.
Yeah.
And some of them are in tilted orbits, and some of them might even be in retrograde orbits like Triton around Neptune, where they're captured objects. So those showed up later. But these main moons probably formed, early on when the plane of this whole thing was already tilted.
Mm-hmm.
And you can see that they're bright enough that they're showing those diffraction spikes, the characteristic multiple spikes from James Webb there.
Right.
Well, gentlemen, my aging brain is having trouble remembering what the device is called that keeps things level like airplanes. That you can't.
Gyroscope.
What is it?
Gyroscope.
Gyroscope. That's a principle, isn't it?
Yes.
Something that's spinning is hard to turn.
And that's angular momentum. Yeah.
Yeah, exactly.
Oh. Okay, but only one telescope on the planet, Keck, got a picture of those rings. None of the rest can get them.
Well, they were seen by the Kuiper Airborne Observatory also as occultations.
That's an observatory in a plane?
Yeah.
I think it was a 747.
Back then, no, it was a C-141 Starlifter, I think.
Oh, okay.
How the hell do they keep things steady in an airplane?
Yeah, gyroscopes.
Gyros.
Stable platform.
Okay, got it. Well, Uranus, you're the runt in the solar system of gas giants. Ooh, here's that giant, huge galaxy.
This is Rubin's galaxy, Vera Rubin. This is one that she studied to measure the speed at which things were rotating around the galaxy. And she noted these stars here, this one and this one are, and I think the brighter ones there are in our galaxy. This galaxy and that, and then some of the fainter stuff, the red stuff, that's other galaxies. But she studied this one to measure the speed of everything. And she did that by looking at different parts of the galaxy with a slit on a spectroscope and measuring the Doppler shift of the lines for each of these regions. And the speed she came up with confirmed Zwickie's back of the envelope calculation that there was missing mass. This is the observations that she made on M33. This is a different galaxy now. It's the one I use in the background for me. These are observations from the starlight in the galaxy from 21 centimeter hydrogen, which we covered a few weeks ago where that comes from. And it's not associated with a star, it's in the gas. It's the gas between stars, which the galaxy is loaded with.
And it's kind of those red patches that you see there.
Yeah, and it's a radio telescope, not a visible telescope. And this is the path that you would expect from Newton's law of gravity for particles orbiting this amount of mass. There would be a very high speed as you go out, and then it would drop off as you go to higher energy but lower speed orbits. So this is where Newtonian gravity doesn't work for this case. That's where they came up with modified Newtonian gravity, which does work in this case, but it doesn't work in any other case. And so the present hypothesis, which there's a lot of evidence to support, is there's mass in this structure that we don't see. And the mass is more out here in a donut shape than it is concentrated in the center, where the visible mass is concentrated.
And by the way, there's one of the planetarium shows that's now at the museum is Dark Matter, Phantom of the Universe, and it's about the search for dark matter. And there's kind of a funny bit in there where they mention one of the first indications that this dark matter is out there was Fritz Zwicky, like they mentioned Vera Rubin, here sort of confirming what he saw. And they put up something that at first looks like a nebula, and then as it rotates around, it's a picture of Fritz Zwicky, and he's pointing one finger off like this, and with his other one, he's doing this. And that's kind of referring to the fact that he was considered kind of curmudgeonly, and and he was talking about dark matter, that he was seeing, and people were saying, no, that can't be. And he started to describe other astronomers who were criticizing him as spherical bastards.
That's right.
He says, and so he was making that sign as they're spherical because they're bastards no matter how you look at them. Whatever direction you pick, they're symmetrical.
So this is a graphic of two galaxies. Can you see this?
Yeah.
Okay. So this is what we would expect to see from Newtonian gravity. The center is rotating faster, and as you go farther out, these stars are rotating slower and slower, and you see their velocity is dropping down. But what we actually see is that the stuff out here is rotating much faster than we would expect. It doesn't really decrease in speed significantly as you go out to the edge of the galaxy.
I'm sorry, they seem to be looking the same to me.
Well, look at this one and this. Well, where would it go?
Oh, I see. Okay.
See, they're going.
There you go.
This one's just dragging its feet. This one, but the center is going the same. But the edge ones are really moving slow.
So that's what gave us the inclination. There's
dark matter. Dark matter distributed out here.
Invisible
sort of in a halo. They call it the dark matter halo. It's a donut shape.
Well, is this the Rubens we're looking at?
No, this is a mathematical model made for demonstration purposes.
Okay, but the Rubens is 10 times our size, but laid out about the same, two major arms.
I don't know about 10 times our size. That would be a huge galaxy.
Well, we're 100,000 light years across, and it's 800,000. That's almost 10 times.
Yeah, I think we're considered more like 200,000 light years across these days.
Oh, catching up with Andromeda.
Well, I think Andromeda is about the same size as us.
Yeah, that's the current thinking.
This galaxy, Rubens galaxy, is UGC. I forget what the U stands for, but GC is General Catalog.
Uppsala
Okay.
General Catalog.
Thank you. This is 232 million light years distant, and it is 800,000 light years across.
Wow, that's huge.
It has 1 trillion stars, which is about 10 times what they used to think the Milky Way had when the Milky Way was 100,000 light years across.
Okay, so it is very large.
Yes.
Well, they also, don't they think that Andromeda has like 1 million stars?
Oh, a million, yeah.
Well, 1 trillion solar masses,
Oh,
probably
okay.
4 stars.
Yeah, no one's counted the stars. Let me be clear on that. But a very pretty galaxy.
Yeah. And of course, she picked it because of this orientation, so you can see
right
leading and trailing parts and quite a bit of the disk.
Mm-hmm.
Well, given enough time over the eons, the arms are going to stretch around, and it's going to.
The arms are transient features; they're not solid, so they don't kind of wind up.
Well, they go slower. He just showed us that.
The stars in them go slower, but they pass in and out of those density waves.
Mm-hmm.
If you watch in that simulation, you'll see some dots that just pass right through the arms.
It's hard for me to go back to that, so we'll have to remember it.
Well, yeah, but it seems to me similar to the situation on the sun with the different levels going different times or different speeds and ways. You follow what I'm saying?
Yeah.
And after a while, it just snaps and gives us a
Well, those are
prominent-
magnetic field lines. Yeah, they're connected, and so they stick together. But individual stars aren't like that.
Yeah, these are not solid objects, or permanent objects. As Chuck says, they're transient. The arms are transient.
But the big elliptical galaxies, which are just balls of cotton, they're not moving at all.
They are moving, but they're not moving in an orderly fashion to produce arms.
Yeah, it's like globular clusters. It's just
Yeah.
random orbits in there, like bees flying around a hive.
Okay, so an elliptical could be an oval, a circle, or a sphere.
Yep,
They're
any of
generally
those.
spherical or football shaped.
Right.
Okay. And they didn't start out as spiral galaxies, and sometimes they get made when two galaxies collide. You get an elliptical, don't you?
Right. If you look at Centaurus A, you can see there's a spiral with dust lanes that has collided with another galaxy, and it's sort of forming an elliptical, but there's still a lot of gas there.
And then I heard that somewhere out there they found a few galaxies with no dark matter in them. How in the world do they know that? Same way.
They have found ones with no dark matter, and they've found ones with only dark matter.
Only dark matter, then we couldn't see them.
That's right. Well, there's other ways to see them.
Gravitational influence on things around them, so you can determine if they're there.
We'll have to look at those, the dark matter galaxies.
In the future.
In
What
the
is
future.
this? What are we looking at here? Jerry?
This is a radio telescope picture of Centaurus A down here, the center of our galaxy.
It's
and you
Sagittarius.
see-
Sagittarius A
So
star.
yes, sorry, what did I say?
Centaurus.
Centaurus, okay. Sagittarius A star.
Can't believe I corrected the president instead of Chuck.
Oh no, I screw up all the time.
That's all right. I'm glad we're all human here. That's the black hole or we're looking at?
Well, yes, but the key thing of the picture is
the
the
arcs.
recently discovered smooth, gentle arcs that are in there. This is a highly magnified region of our center of the galaxy. And these are believed to be plasma streaming along magnetic field lines, smooth magnetic field lines.
Wow.
More to come on that. That's called the Galactic Center Radio Arc.
So it's a large,
The curving filament is known as the arches.
this might be a larger version of what comes out of our sun, except this is from the accretion disk.
This is not, I don't know the temperature of this stuff, but it glows because the plasma is moving along the magnetic field lines and it collides with nearby cloud of cold gas, and that causes the emission. But these are very long, very big magnetic field lines. So there's magnetic field lines all over the place.
And somehow a radio telescope can see magnetic field lines.
You
Well,
can see the effect of them.
Yeah.
Obviously, your optical telescopes can't see any of this.
Well, neither can the radio telescopes. The optical could see, you're seeing the effect of the magnetic field lines.
Well,
You can't see them directly.
That's
I'm
right.
looking at a picture. Is this an artist rendering?
No, this is a picture made by radio telescopes. It's what the universe would look like. The core of the universe or the galaxy would look like if you could see radio waves with your eyes. You would see this.
Is it only on one side?
Well, only the side we can see. The other side we can't see through to see if there's something over there.
So it would be
Picture this: a stream of particles moving along these magnetic field lines, and they run into particles that are stationary, that are sitting there. And when they collide, they absorb energy and then they re-emit it, and it's that energy that we see from the collision. So, as Bruce pointed out, it's not the magnetic lines that we see, but they are following magnetic field lines. So like when you put a magnet under a piece of paper and you put iron shavings on top of the paper, you don't see the magnetic field lines, but you know that the iron shavings line up with the magnetic field lines, and it shows you where the magnetic field lines are. So this is like that. It shows us where the magnetic field lines are.
Well, My understanding is that magnetic field lines are on spinning objects like the Earth and the Sun, and they come in on the poles. Would that be how it goes on Sagittarius A?
That's a special case of things. Magnetic field lines do not start and end on a charge like electric fields. They are generated as a loop around moving charges. So if you have a charge moving from right to left, then you would have a magnetic field line. If the charge moves this way, then you would have a magnetic field line moving this way around the charge as it went, like a halo around the charge.
Whoa.
This is the vector sum of magnetic field lines that you see there. Whoop, no, my pointer. This is the vector sum of magnetic field lines from a lot of moving charges far away that generated it.
Yeah, see, in our case, like with the Earth's field lines, you have sort of a source that's confined within the Earth, that is the nickel iron core that's got convective patterns in it, and those moving charges generate this magnetic field. And so from our point of view on the exterior, it looks like there's a source down there and they loop in and out of it. But here you've got a more chaotic generator. And so it doesn't necessarily form those nice patterns.
So SAG-A doesn't have any auroras on its north.
No, this is exactly what it is. It's an aurora.
Yeah.
Is that right?
In the Earth's case with aurorae, they come in from the sun and they collide with the upper atmosphere of the Earth and they emit light. This one is the ions come along, driven by magnetic fields again, and they collide with particles that are there and they emit light. So it's like a galactic aurora.
Wow.
Except the light is much lower frequency than visible light.
Yes, yes.
Well, that's what infrared is, isn't it?
But this is radio, even
Yeah, this is
radio.
beyond that.
Well, this is radio waves. It's down in my broadcast range. So
Well, they're in the microwave range, but
right. So that's not part of a shell around the black hole. That's actually in space. just
We don't have, this is a first discovery look at it. We don't know the entire shape. But for example, magnetic field lines do not just suddenly start and stop. When you see something that is like that, you know, it has to be somehow a loop. It has to be all contiguous. We'll probably map the structure and in more detail as our instruments get more sensitive.
yeah, we've never found a unipolar magnet, a one-pole magnet.
Yes,
we can't
magnetic monopole.
Right.
Yeah.
we can't really see magnetic lines of force. They got to be something in there like iron filing. So everything you're seeing in this picture is matter that's being affected, right? That's all part of the accretion disk, all that stuff on this picture.
No, the accretion disk is way down close to the black hole.
There's a lot of, go ahead.
Go ahead, Chuck.
Oh, I'm just saying there's
So
the accretion disk is way down close to the black hole. This is much farther away.
But the bright thing in the bottom is the black hole.
Yes, that's the accretion disk down there.
Or the region, yeah.
Yeah.
Oh, okay.
There's a lot of chaotic structure going on here too. There's obvious solar winds blowing dust particles or molecules away, hydrogen. So since this is radio waves, I suspect that everything you're looking at here is in some way hydrogen.
And those little blobs you see that are semi-spherical, those may be supernova remnants and things like that.
Yeah, there's a lot of structure in here. But these arcs here, this is like solar wind blowing things away, pushing away.
Well, that'd be stuff from the accretion disk then, wouldn't it?
No, that's way down there in the bright part of what you see down below. Way down there.
Accretion disk would be, you can't see it, it's too small on the scale.
Well, I see
These
something
are like a
right.
coronal mass ejection. They've already left the sun, and then the sun can't pull them back.
Yeah.
Well, Sagittarius A, they say is a star, but it happens to be a star we can't see called a black hole, a supermassive.
Yeah, but we can't see its accretion disk. Yeah.
Well,
and that's where this energy comes from.
Okay.
So it's probably tilted this way.
Well, that's how they determined where the black hole in the Milky Way center is, by looking at the orbits of things around it.
Well, those two pictures that we got, one of ours and one earlier of a distant galaxy, shows the bright hole in the middle and kind of three orange blobs around it. Remember that?
Yeah.
How they looked? That would be too small to fit in this picture, I guess.
Yes.
Interesting.
Way
Gentlemen,
down in that bright part.
Yeah.
well, you have dazzled me again. I hope you've dazzled the viewers we might have, and I hope we got some of them from Friday night. And last night you were out at Bacara. Let's get a report real quick. What happened? You had the fog early on?
There was a wall of fog. You know, it was clear here in Goleta and Nolita. And as we drove up, there was a wall of fog right at Bacara. But we set up, and by 9 o'clock, it cleared out. It was clearing from west to east, and it was a beautiful night after that.
Okay.
All right. We're into our second week of the month of April. What's in the immediate future?
We got a couple of schools, but the next sort of public thing is probably Telescope Tuesday. Oh, no, first is Westmont on Friday, the 21st. And then Telescope Tuesday at Camino Real Marketplace on the 25th on Tuesday. But the big thing is International Astronomy Day on Saturday, the 29th, from 10 a.m. to 10 p.m. at Camino Real Marketplace.
When you say Telescope Tuesday, you're not talking about the program that we have, another Zoom on Tuesdays. Is that still airing?
No, Telescope Tuesday is the fourth Tuesday of the month when we set up telescopes at Camino Real Marketplace.
Do we still meet online though, once a week? Talk about telescope?
That's a different function. That's the telescope workshop where it happens on Tuesday night, every Tuesday.
Workshop, and it's still going on. You can tune that in tomorrow night. Gentlemen, we'll do number 113 next week. And it's been awesome talking to you. Take care of your wives and your cats and your lives, and don't speed in those Teslas. We'll do it again for the Santa Barbara Astronomical Unit, SBAU Astro Hour. See ya, everybody. Thank you.
Thanks.
Bye.